Assalamu alaikum, dear students. So today I'm going to explain you a very important topic in statistical mechanics, that is the effect of temperature on the rate of reaction. Effect of temperature on the rate of reaction. So the first effect of temperature on the rate of reaction was explained by Huth about 100 years ago. Later on, Arrhenius modified that equation. So the first equation was that is given by Huth about 100 years ago. That was log of rate constant is equal to A minus B over T. Where case the rate constant B is a constant and A is constant, while the T is absolute temperature. So these A and B are empirical constant. Later on in 1889, Arrhenius modified this equation and that equation is natural log of K is equal to ln K is equal to ln A minus EA, where EA is activation energy, divided by RT. R is ideal gas constant and T is absolute temperature. So this is one form, in exponential form, K is equal to A E power minus EA over RT. So this is the exponential form. So these are the three equations. The first one is the early equation about 100 years ago. It is given by Huth. Log K is equal to A minus B over T. So this is the first equation. The second equation is natural log of K is equal to natural log of A minus EA over RT. So this is the second equation given by modified by Arrhenius, and the third equation is the same form but is in exponential form. K is equal to A e raised minus EA over RT. So these are our core equation. We have to use this equation continuously during our discussion. So generally it is stated that the rate of reaction doubles when we increase the temperature with the 10-degree difference, such as if the initial temperature, the difference between final temperature and initial temperature is 10 degree, so the rate of the reaction doubles, that is K2 over K1 ratio is 2. This is true. This is a very general phenomena. This is true because most of the reaction they are taking place in a very narrow range of temperature. That is the temperature range for these reactions are between 30 degrees Celsius to 40 degrees Celsius, or this is some kind of room temperature range. So in this case, under this condition, the statement is true that the rate of reaction doubles when we increase the temperature with a 10-degree difference between the initial and final temperature. So the rate of the reaction double. And under this condition, if we take equation number 2, if we plot natural log of K versus 1 over T, so the behavior is linear. We are getting a very linear relationship. We are getting a straight line with a negative slope. So the relationship is quite linear. But there are several cases in which the reaction are taking place over a wide range of temperature, and this statement is not correct. So the behavior of rate constant or the Arrhenius behavior is not valid, or the uh, behavior deviate from the Arrhenius behavior. Uh, for example, if we this is true only when we have the activation energy uh, that is EA is equal to 50 kilojoule per mole. But if we study the reaction over a wide range of temperature, this behavior is not correct. So if you choose, for example, in equation 2, if you choose uh, activation energy EA is equal to 100 kilojoule per mole, and now we have precondition. If we choose the temperature that is 1000 Kelvin and put in equation 2, and we calculate the rate constant, we solve the equation number 3. For simplicity, we will take equation 3. If you put the temperature 1000 Kelvin and activation energy 100 kilojoule per mole in equation number 3, and calculate the value of rate constant K, so the K value will be K is equal to, this will be 6 into 10 raised minus 6 A, where A is Arrhenius constant, the same one, we just solve the exponential term. On the other hand, if we increase the temperature further, that is, we take 2000 Kelvin and we solve the equation 3, so the rate constant value is increased, and that is 2.4 and 10 raised minus 3, it almost double, whereas Arrhenius constant. And again, if you are increasing the temperature too much, that is 10,000 Kelvin, so the rate constant value will increase to 0.3 A. Similarly, if you are going on increasing the temperature, and if we reach infinity, that is the temperature reach to infinity. So if you put in that exponential term, so the exponential term, that is 1 over infinity, and this 1 over infinity is 0, and this E 0, we are getting 1. So the rate constant will be equal to Arrhenius vector. So this is a phenomenon in which the rate constant actually increase if you are varying the temperature. And this behavior, if you plot ln k versus t, so we are getting a sigmoidal curve. In that case, if we are studying the reaction rate over a wide range of temperature, not on in a narrow range such as 30 to 40 degrees Celsius. So if you plot ln k versus 1 over t, so we are getting a sigmoidal curve. So it looks like a sigma sign. So this is deviating from the linear behavior. Now there is a question that what are actually the factors which affect this linear behavior? Why there is not a linear behavior? What are the specific factors? So for the specific factor, we are just considering the activation energy. So what are the specific factors which affect this linear behavior? For that, we are taking equation number 2 and modifying that equation at two different temperatures, such as just taking equation 3 at low temperature T1. So equation 2 will be ln K1 is equal to ln A, this is constant, minus EA over RT1. So this is our equation first, for example, and at high temperature T2, so ln K2 will be ln A minus EA over RT2. Now just subtracting the lower temperature value from higher, that is subtracting K1 from K2, so ln K2 minus log K1 is equal to, these are the two terms A, so that will be cancelled, or we can write down ln A minus ln minus EA over RT2, high temperature minus ln A, so these two will be cancelled, and this minus will become plus EA over RT1, or just simplifying this, ln K2 over K1 is equal to, just modifying, so we have to take EA over R as constant, and we have 1 over T1 plus, and this 1 over T2 is minus 1 over T2. So, or we can write down in another form, just taking LCM from the variable term. So we have T2 minus T1 divided by T1 into T2. So this is our previous equation we already derived in our first chapter. So this is some kind of straight line equation. We forget about for a time being about intercept, but this left hand side is y variable, and on the right hand side all the things we have to keep constant, and only activation energy is varied, that is activation energy is we took as x. So this is and we took as an independent variable which doesn't depend on anything. So if we vary the activation energy, the ratio of the rate constant that will be varied. So just now if we put the value of activation energy in this equation, that is we got this equation ln K2 over K1 is equal to EA over R into T2 minus T1 divided by T1 into T2. So this is our equation number 4. And this equation number 4 we have to explain very important terms, that we just took this as y and this we took as x, and other things are constant. But now right now we have to choose to fix temperature, because other things should be constant. R is already constant, so we have to take a temperature that should be fixed. So the initial temperature we choose T1 is equal to 295 Kelvin, for example, and T2 we just choose 305 Kelvin, or in Celsius term, degrees centigrade, this is 22 degrees Celsius and this is 32 degrees Celsius. So that difference between the two temperature del T is fixed, that is 10 degree. So now if we are varying the activation energy, for example, just we choose two cases. The first case we choose activation energy, that is EA is equal to 50 kilojoule per mole. So what will be actually the ratio of rate constant, and if you put in equation 4 the temperature T1, T2 and activation energy 50 kilojoule per mole, so we are getting the ratio between the two rate constant, that is the ratio between K2 over K1 is equal to 2. We are getting 2. On the other hand, if we in the second case, if you put the activation energy value EA is equal to 150 kilojoule per mole, that is too high as compared to the 50, almost 3 times. So the ratio of the rate constant calculated from equation number 4, that is K2 over K1, in this case we are getting almost too much high, that is 7.4. So if you compare that, this is actually the activation energy that affect the rate of the reaction. So if you have highest activation energy, the rate of the reaction or the reaction is faster. Now we have two variables, so this can be easily plotted on y-axis and x-axis. So we just choose that our K2 over K1 we can plot on y-axis, or K2 over K1 ratio we can plot on y-axis, that is, and on x-axis we can plot activation energy EA in kilojoule per mole. So this is x-axis, that is independent variable. When we are varying the activation energy, our rate constant value vary. So just take activation energy on this side, that is 20, this is 50, this is 80, this is 100, and this is 120, and this is 150 kilojoule per mole. On this side, This is our origin, so everything is 0 here. This is 1, this is 2, 3, 4, 5, 6, 7, and 8. So now we just solved right now that when we have the activation energy 50, so the ratio of the two rate constant is 2. So we got 2. And if you are increasing the activation energy, when you increase the activation energy to 50, 150, so the ratio of two rate constant was almost 7. So this we are getting some kind of curve. When we increase the activation energy, the ratio of the two rate constant increases. So we got this kind of curve. So the important factor is the activation energy. When we vary the activation energy, the rate constant vary. Now we have another phenomena in which we can again take equation number 4, in which we plot the ratio of two rate constant at high temperature versus a lower temperature against fixed temperature, that is the temperature vary, and we just fix the activation energy in equation 4. So we just take this temperature as x variable. In the second case, we just take this temperature as variable on x-axis. So what will happen? We fix the activation energy in this case. So when we plot K2 versus over K1 versus temperature, and this is average temperature. The temperature vary from each other by 10-degree difference. So just taking this ratio K2 over K1 on y-axis, and this average temperature in Kelvin on x-axis, and when we plot this at fixed activation energy, in the first case, let's activation energy we are taking EA is equal to 50 kilojoule per mole. So what will be the effect? Just take the temperatures. It's from 200 Kelvin. This is 220, 240, 280, and this is 300. This is 320 Kelvin. On y-axis, this is rate constant 1, 2, 3, 4, 5, 6, 7, 8, 9, etc. So if we take activation energy 50 kilojoule per mole, so if you are weighing the activation energy, so if we are keeping the activation energy constant and we are varying the temperature, so what will be the effect on the ratio of the two rate constant? So when we increase the temperature, so the ratio of the two rate constant decreases, and if we take two temperatures that are differ from each other by 10 degrees, that is our previous case, 295 to 305 in this curve. In this range, if we want to find out the ratio of the two rate constant, so for this activation energy, that is 50 kilojoule per mole, we got the rate constant, the ratio of two rate constant 2. So in this case, we got 2. Now if we want to study at a different activation energy, fixed activation energy, the ratio of the two rate constant against temperature, average temperature, that is another activation energy, fixed activation energy, that is 75 kilojoule per mole. So if you plot, so this plot will look like here, and the rate constant measured, that is 3 at this temperature. So the rate constant we found, the ratio of the rate constant, if we increase the activation energy, that is for the second case we got 3, and for the first case we got 2, and if we again increase the activation energy and keep that fixed, and we want to see the effect of varying the temperature on the on the two rate constants, that is we increase the activation energy and fix to 100 kilojoule per mole, and we study, then we are getting the ratio of two rate constant is 4. So this is the two rate constant 4. So this rate constant actually look like that if you are increasing the temperature, so the ratio of the two rate constant, the difference it become narrow. That is there is a very little slight difference at high temperature between the ratio of the two rate constants. Uh, that is high temperature and lower temperature. So we got here 4 in this case, K2 over K1 is 4. In the 75 we got is 3, and in the 50 we got the ratio is 2. So this is another way to see the effect of temperature on the ratio of the two rate constants. So we have studied the effect of activation energy on the ratio of the two rate constant and the effect of temperature on the ratio of two rate constant. And this is particularly for those reactions which are studied under a wide range of temperature, not in a narrow range of temperature, that is temperature is higher than the room temperature. So